Welcome to the Evidence and Reasons for the Christian Faith video channel. I'm Salvador Cordova. I'm privileged to be joined by Peter today. He has a presentation on some population genetics material, and so I'm really thrilled to be with him today. I need to pause 1 second. And so we'll just go right to it. Peter, could you say a little bit about what your presentation is today? Thank you.
Okay. Hi all. So my presentation contains its result of some simulation done in Python, computer language. I will explain the. Okay. So okay. I'm gonna explain now some basic maths. What, of course, you know that, but it's just for watchers of us, so they understand the basic about it. And then I will explain my result. I will define my simulation, what I make in the program. I will explain result. And then I would like to, if it's possible, I would like go into my program and explain this. So you see the details, and you see that like everything is fair. And maybe we can discuss results and maybe it is possible how to modify this program. So is this program is this program relevant to describe real events or not? So how can you change it to make it better? So that's it. Okay.
Well, that's outstanding. There were some math results that Peter arrived at that I was very impressed with. This regards to Muller's limit. Muller's limit, Peter and I did some videos on Muller's limit, and we're going to, he offered to do some simulations. There are some things with Muller's limit that are very interesting, and Peter made some very brilliant he independently arrived at some math conclusions that a famous population geneticist, James Kreo, arrived at. There's some really great math that I was not aware of, and I'm going to share that today as well. So,
yes, but what I wanted to say, it is not like a formal conclusion. It is the results of the simulation what put. So I would be glad if you can point to that if there is a formal solution, like with formulas or something, because I do not know that. I know how to construct the program what makes that, but I cannot solve it formally.
That's great. And if we have to go to another show to work out the formal stuff, we can. I don't know that I'd be able to do it myself, but I am aware of it, and we'll move forward. Let's just go into your presentation. And thank you very much for your kind words, Peter. I'd also like to, I'd also like to let the viewers know, I want to say thank you very much to all the viewers for their well wishes for my mother. She was gravely ill. I thought she had to go to the hospital, and if she did, they probably would have sent her home to die with hospice care. We found a cure for her urinary tract infection. At her age, at 94, even some things that someone young could easily tolerate could be fatal at that age. I was able to find a particular carbohydrate, a saccharide called D-mannose, that inhibits the ability of bacteria to attach to urothelium cells in her urinary tract. So even though it doesn't kill the bacteria, it allows it to flush out with enough fluids. The problem was she was developing antibiotic resistance to some of the bacteria, and we had to look for alternative cures. And so providentially, I happened to work with a professor at the medical school at Vanderbilt University, and one of his colleagues had specialized in the area of bacterial adhesions, and this all just came to the cure arrived this past Wednesday after some research on my part, and then looking at the various medical literature. So I'm just updating all the viewers. Wanted to say thanks. So now it makes it possible for me to be with Peter today. Anyway, so some mathematical background. We're just going to look at some common distributions, the binomial and Poisson model of distributions for of mutations for a child, its applications to Muller's limit, a short overview of previous content, details discussed, considering part 1B, and then computer simulations, additional materials, questions, and open discussion. I want to say I learned something, Peter, that I didn't know.
Mm-hmm. What?
And that was, I'm going to just give a preview of the slide. There's a connection between the Poisson and binomial distributions. I didn't know that.
Yes.
So thanks to you. Did you know that before you started studying?
Yes, also, as I know, actually the Poisson distribution comes from binomial distribution by having the limit. So it is basically per definition of mathematical sense of Poisson distribution what it is.
That was spectacular. I did not know that. I did. Yes, I absolutely did not know that. So I looked it up and I was very impressed. So I'm just going to share. So I'm just going to share that with the audience here. They can Google this. There are various ways you could find it on the internet, but here's the proof. It says the Poisson distribution is actually a limiting case of a binomial distribution when the number of trials n gets very large and p, the probability of success, is small. As a rule of thumb, if n is greater than 100 and n times p is less than 10, the Poisson distribution, taking lambda equals np, can provide a very good approximation to the binomial distribution. And there's a proof here. So I learned something. So now I'm really glad that you did this. So that was fabulous. So thank you.
Yes, thanks. But I instantly see the mistakes in the slide. Maybe I can screen share and it would be better so I can correct.
Okay, I enabled your screen share and go ahead. This is an informal meeting. So this is great. This is like a learning session for all of us. I enabled your screen share, so you should be able to post it.
Okay. So do you see that?
Yep, I can see it. So we can edit this on. That's fine if you want to edit it.
Yes, because maybe it was actually long ago. Maybe I added some material, but I will explain. So, what is the sense of binomial distribution? It is the probability distribution of the number of successes. If you make, for example, n of independent experiments, like you throw a coin or you throw a, what is the name of it? If you make some experiment with a probability of successful experiment, and so one minus p will be the probability of unsuccessfulness. So, and you wanted to figure out what is the probability of this many experiments to have together k number of success. It is derived like that. It is written like bin and k and p, and is so brackets n and on the k it is the what's the name?
The combination. I think that's a combination.
Yes, it is combinational coefficient because the number of variants to place car elements among n is this number. And also each variant of those has a probability p times car minus 1 minus p n minus car. And with the most plausible value or expectation value is this. If you wanted to have what value will likely to be, if you make very many experiments, it will be n times p.
That was great.
Yes, but you have also some possibilities that the result will be more or less as expectation value. It is the standard deviance or sigma. Like here, if you see here, for example, if you see the red line, its expectation value is 20. So this probability of 0.5 and 40 experiments, this expression value, but also there is some probability that the amount of results will be more, successful results will be more or less as 20. It is described actually on this diagram.
Peter, I have a question on the graph.
Yes.
The x-axis is the number of successes. Oh, number of experiments.
Number of experiments and no, it's number of successes and vertical axis is the probability of it.
Ah, yes. Okay.
Yes.
Thank you.
Also, to make it probability, the entire sum must be equal to 1. So if you take this curve and count area under it, sort of integral of this curve, it must be equal to 1.
Yes.
So it is principle of probability. Yes.
And so that's the binomial distribution there. That graph would be a binomial distribution.
Yes.
I should point out to the readers also there's a relationship between the binomial distribution. It can be approximated by the normal distribution, and that can come in handy. So if the graph looks familiar,
all those distributions are actually some variants of normal distribution because it has the same form. I have seen. So that.
And I should mention to the listeners, I'm not a statistician or a probability guy that much. So it's good to be acquainted. My math was in a totally different specialty, but this is still fun. So thank you.
Yes.
Go on, Peter.
I have it sometimes in some projects. So I know it. So how would I explain the Poisson distribution? So very short, but so let's imagine you make binomial experiments with many experiments, such as n goes to infinity amount of experiments, and very low probability, such as probability of each experiment comes to 0. But together, n minus p comes to some constant. In this point, it is 2. For example, it will be if you have huge population, and the probability of each organism to have one mutation is very low, but together n times p is equal to u equals to 1. Okay? This can be approximated by Poisson distributions, so it stands here normally. So basically, this formula, like right here, is numerically equal to this if n comes to infinity, because there is some formal explanation for this. What I have skipped. It is some limit of these brackets. Limit of such brackets in the some power. This goes to exponent. There is some limit formula and other stuff. This is how to show it. But I have skipped this because it's not important. It's just so the example is listed here. What I mentioned. If there is one, in average, one mutation per organism in population, that means for That means that P is equal one times n. And you can take it like binomial distribution like this. And it gets closer to the Poisson distribution as the population size gets bigger. That's because for big population sizes, they count it in Poisson because it's numerically equal. So,
Well,
and how, yes?
Oh, that was great. I like I said, this presentation was brilliant. I learned something.
Okay, so this is, it is very good if even you can learn something for that. So, okay. So it, and to how do you simulate this numerically? So you make actually n population of n units, like you have an array in your program and you randomly assign them once. You must assign them once u times n times. And the sum of each unit will be Poisson distribution. That means, for example, you have population of 1,000 units, okay? And say in average, each unit have probability of having 2 mutations. And how to simulate that? Very simple. I just take 1,000 units and randomly each time I pick one unit randomly and assign them 2,000 mutations. And the resulting distribution will be Poisson. K is what is K?
Mm-hmm.
And the resulting distribution will be Poisson K and U equals to 2. This is how I made it in my program. Okay. Was it understandable? No.
So in your program, did you use the binomial distribution or the Poisson function to implement?
I use it numerically. It actually doesn't matter because I simulate real events and not
Okay.
this distribution formulas.
Okay.
And I just told how to simulate this event. You take population of n units, and if you have like U is equal to 2, like in average each unit have 2 mutation, you assign randomly 2,000 mutation to the population.
Okay.
And this will be this Poisson distribution. So actually, I have done numerical simulations. That means I have not used these formulas. I have simulated the events inside of population.
Okay.
This is how it was. Okay, now, further, as I studied that, I come to the questions: what amount of mutation will have a child of some parents? Because if you view your model with Muller's limit, like you have generation of some units, you assign the mutation, and then you have new generation. Okay, so you must think about what mutations will be there because these are children of those who was before. If you do not think of that, you have like in next generation sort of clones of those. You just copy the same units and assign them and assign to them new mutations. This what I show later. These two approaches can lead to actually different dynamics. Like in one case, the average amount of mutation will increase. In other case, decrease, depending of different parameters. Okay, so let's take the following model. An organism is represented of the genome by having an array of some large n of zeros and ones. Example 0, 1, 0, 0, 1, etc. And 1 is on the place where this gene is mutated, and 0 it is not mutated. So if you calculate how many mutation have this unit, you just sum over this array in the program. So now you have two of those organisms, for example, parent 1 and parent 2, with K1 and K2 mutations already present in random places of them, So, and you have the questions, what mutation will the child of this have? If each genealogy comes to the child with 50% of probability. So like this, if the parent 1 is have this genome and parent 2 have this genome, first random child can have actually one mutation of this, and on these places it can be zeros. So it is randomly here 0 from the pair 1 and 0, and on this place it can be 0 from the pair 0 and 1.
I just, for the viewer's sake, the term they sometimes use is random gametic sampling. So they can, when the two parents have a child, it can take the gene either from the mother or the father, and so that's why the random child could either, in one case, it could either have inherit from the mother or father. So therefore, it may or may not be mutation free, unless in the situation both parents happen to have a mutation at that locus, and so that's
Yes.
reflected. Yep.
But I actually am not sure that this model is pretty detailed, like what actually happened, because what I said, there is so how recombination happens. It happens like there is exchange between huge places of genome and not one gene, and there can be some, I don't know, duplication and other stuff, like one gene is copied twice and so on. We can discuss it later in order. So the one point I wanted this conversation with you is that you point to me how to make this model better, because I'm not sure that this is correct. So what's your opinion?
I think that's the way I've seen it in population genetic literature. It's a close enough approximation.
Okay.
Yeah, it's mechanically it works out, even with what they call recombination. It's a good enough approximation. I don't think that any there's subtle things there that actually may not be important at this in models like this. This should be good enough. That's my understanding.
Okay, thanks. So what I wanted to say also, the one can take models that you take amount mutation of both parents and take average of it, and it is that this is the amount of mutation what child have, but it is actually naive, because you skip the details that some child can have less amount of mutation and some child have more, and really this feature influences on the dynamics.
Yes, that's what you've arrived at is actually a very important result, and ironically, I think this is also it'll actually follow a binomial distribution.
Yes, it is some, but I have not figured out. It is not binomial. It is not binomial as much. You can approximate it as a binomial curve, but I'm not sure what parameters are there.
Oh,
so it's just this normal distribution curve.
Okay.
What happens in all kind of this kind of distribution. I would really wanted that this task which solve mathematically.
Well, I if I could just tell the viewers what's going on here.
Mm-hmm.
There will be a situation, let's say we have parents and they have a huge number of children, just hypothetically, let's say they have a huge number of children. There'll be some children with lots of inherited defects, and there'll be some children without them, and it'll follow a normal curve. So that's actually an important result, and that's something that we'll see later on in Peter's presentation. I had the opportunity to look at some of the slides before. I was very impressed.
Mm-hmm.
So that's one thing that you're pointing out is an important result, that you can have, even though the average number of deleterious traits, I'll use the word traits, like say parent one and parent two have two, they can have children, they can have a child with just one and another child with three. The average is still two, but that's an important result right there.
Yes, and if you make some population dynamics, you may not approximate that as just half. If you erase some real data, what is important. So may I go fast? So okay, so I have not solved it formally because it is some tricky probability theory task. I can, if we have time, I will show later my solution, what is not complete there. So, however, I simulated it numerically in Python. Like I just actually generate many parents, and then I get a statistic about it, and then I make from it the plots how it is distributed. For example, imagine you have gen loci size of 200, so you have both parents, this arrays of zeros and ones is 200. One parent have 80 mutations, one parent have 120 mutation, but they are in different places in location. And then you simulate these calculations and you get a statistic how it is distributed. And it is distributed something like that.
That's what I would expect. It looks very nice.
Yes, yes, it is some normal style distribution. You can actually numerically figure out what the parameters are. So how to say it? Approximately, yes. So you have the as expectation value you have the average value. So 80 and 120 is average is 100, and it is distribution something above and below. So, and the important part of this is that children would have less mutations than most of parents. This makes the population dynamics like this, like I will show. So I'm gonna repeat Muller's limit short of it and its connection to the math what we have before. So the thing in Muller's limit that there is needed to A times U minimum number of offspring per pair, where U is the average mutations per organism. So, so to say, you want to Poisson distribution produce zero mutation, or else you think you must eliminate the organism because this organism will have one or more mutations. Like Poisson distribution from this formula, what we have, and you just substitute zero. So you want to see what is the probability of this distribution to have zero children, and it will be A times minus U, what for big U will be a very low number. That's why because the probability is low, So you calculate that you have in average that you must in average to have Adams or children to get one child with no mutations, and 2 times this if you want a pair of parents to produce 2 children. This was in the presentation before, right?
Right, right. And
Okay.
we derived that. And I also wanted to thank you for your interest in that topic. You're one of the few people that would go into that level of detail. So it was also fun having a chance to show that. And yes, you are correct that this is true for one generation, and there's some subtleties here that we'll discuss that you picked up on that are very, very accurate. And that's why I'm appreciative of this discussion.
Yes, because it is important stuff, and it was actually very interesting and funny programming for me. I learned how to solve this task. So if you have some random events and you want to look what is happening, how to simulate that. So this is, I must say that this statement is true for one generation, but if you view dynamics in many generations, you must consider additional facts, because you add mutation to one generation, so to say, and then they mate and produce children, and children will have amount of mutation not as equals at parents, but in other stuff. This moment before must be taken in the account. So as you shown this in your presentation, I instantly thought about that because as I said before, if you have some image in one step, you must think again how this happens in many steps. It is a general principle you must consider. So I done the numerical simulation in the pattern file. So I simulate like 2000 organism, and so say if you initially add this from 50 to 55 mutation per organism in random of 2000 gene lotes in each organism. So, and in my presentation, I have also different kinds of diagrams. I will explain right now. This kind, the above left and down left diagram is is a population diagram. So in the x-axis there are just units. For example, if you take 1000, the unit of number 1000 will have like 50 with something mutations. And also I make these units sorted, so so it is nice to view.
Oh, Peter, I have a question just so I could understand. This is the one diagram I didn't understand. So the y-axis where it goes from 0 to 100, and then you have x-axis that goes from 0 to 2000. Can you explain what the y and the x-axis? I'm sorry, that's where I got lost.
So x-axis is organism number, and y-axis is amount of mutation. So if you view the organism number 500, the organism number 500 will have this amount of mutation, which are on y-axis.
Okay, I think I understand it now. Those are, you had to sort the organisms so that they will...
Yes, it is sort of population view.
Okay, all right.
Sorted by mutation amount. So
okay, nice. And then the other diagram, the y and the x-axis.
Okay, if you make histogram of it, you know what is histogram is, okay? I think yes, so you will get the distribution of the, you will have the probability distribution of this. For example, this histogram corresponds to this population. For example, this, there is 0.2. There is 20% for a unit to have 50 mutation, and so on. 20% for unit to have 52 mutation, etc.
Okay. Okay. Thank you. Thank you.
Got it?
Yep. I think I got it.
And to make it, you just add this. You just add the y-axis into a histogram and divide by population size. You will get this histogram.
Can I ask another question on the diagrams on the right? So if I integrate that, it should equal the area underneath should equal 1?
Yes.
Okay, thank you.
But also it is shown a little bit tricky because this diagonal line, there must be not there because it is just a point. So if you integrate, if there is actually this rectangle from 50 goes up here and here. And area of this rectangle is along horizontal axis. It is 5. Along vertical axis, it is 0.2. And area of this is 5 mal 0.2 is 1. And actually in patterns, they make this diagram smooth and they draw these diagonal lines, what should not be there.
So yeah, if we do a numerical, the equivalent of a numerical.
Strict vertical column there. And
right.
Line. And this
okay. Thank you. It's been a while. So, this is again, this is not my specialty of math, so I'm having to relearn some of this too.
So and now imagine you take this population and they mate once, so each. I just randomly take 2 units from this population. They mate, and you have to, and they produce 2 children. So how the second population would like it will like that, and not. So this it looked like that because of the feature I mentioned before. There is a probability of some child have more or less mutations than parents, and this creates the additional disproportion of the population what you can see now. So there is more of mutation are like average, more of units are in the middle, like average amount of mutation, but some units will have more or less mutations than parents, and then average value of the population. And now if you make histogram out of it, it will be looks like that. What starts to remain of this distribution. And this jumps is because it is simulated, and if you simulate, there is some randomness in the results. So sometimes it will be more or less, but I'm pretty sure you can recognize it. That this is this sort of distribution, because so average value is like 50 with something, 52.5, and around this distribution around it. So what make it? So imagine you have this mutation, and you consider the organism with more mutation are performing worse than those. and you just eliminate those who would have more mutation. For simplicity, let's just imagine you eliminate the half of it. Later, you can adjust, but actually to demonstrate the results, you may consider that you eliminate the half. Is that okay?
Yes, yes, that's fine.
So if I eliminate the half of it, and shown this, the average mutation rate is decreasing because we have removed the worst part of the population. And due to the unequal distribution, there is additional disproportion caused by mating function, what I showed here. We have eliminated more than half of mutation what are existing there. And actually more mutation that was added. Because of that, there is effect that average mutation in the population is decreased. Decrease. And then if you repopulate this, the new population will have similar curve to the first one, but the average population is decreased. So this curve will lie below this curve, like something like that. And you can actually repeat that, and you see that only because of this effect, the number of mutation decreases. I do not consider here that the new mutation is added each generation because I want to isolate this effect. So this effect causes that each unit in each child will have less mutation that you would expect because of this effect. It's understandable?
Yeah. Very good.
So, okay, cool. So later I created the pattern method would run many generations in the loop, and I wanted to demonstrate that this amount is decreasing, and you can view it by calculating the average amount of mutation and actually viewing the curve.
Yes, this was excellent. This was
this curve produce more details. Now, there is, there is some brilliant YouTube tutorials in some stuff. I would create the animation of it, like this curve decreases, but I'm not sure how to make it in
now
Python.
Yeah, now that you explained this part, this was very well done. So very well done.
Okay.
Very good.
So numerically, I got that you can count that there is approximate 3 mutations for each organism per generation are decreased due to this effect. So if you imagine that you add 3 new mutation per organism, it will create some sort of balance because you decrease some mutation by this effect and you add new mutation because of random mutation. How to say that? So what effect causes that new mutation appear for each child? How to say that? You sure? So we consider that each population will have additional mutation for each gene because of random mutation. Just and in this model, I consider on all mutation harmful, and count that I just replace I just have in the Python program I have this arrays and I just add ones in the place of zeros and I count furthermore. Okay, I have another population where I run I run the same thing here, but with added mutation. Like that, I just actually do what a population would probably like. I distribute the new mutation for each step. It is like that. Then I sort of kill some amount of wars. Then I repopulate. That population have initial amount, and so goes on. So in like you can actually parameterize it, like if you have 3 or 4 additional mutation per organism, it still starts to decrease. And if you have for the begin the huge amount mutation, like if you have 10 mutation from the begin, at the average value starts to increase, and then some sort of equilibrium is reached after some time.
What I think that the term that they use is like stabilizes or equilibrium. It reaches an equilibrium.
Yes, it reaches an equilibrium because the amount of mutation increases, and that means that the amount of mutation increases, and this part also increases the amount of children would have less mutations, that their parents are also decreases, what comes again from this brilliant distribution. Actually, all my presentation are based, all my presentation is based on this phenomenon. I would say that.
This was I want to point the readers what Peter has arrived at with his Python computation was a result independently arrived at by other population geneticists. I don't have the citations.
What was I wanted to ask, was it also simulation problem, or have he surveilled the real events in some population? How was that?
I don't, because I only heard this secondhand, and I don't have the actual paper, so unfortunately I won't be able to help you with that. But I knew about this, and I kind of intuitively knew it. But you presented this much better.
Thanks. So I have not knew it, and I just presented it from the understanding from my maths, and
this was excellent. So if I could point this out.
So you would say this result is valid, so to say.
I'm sorry. Can you repeat the question?
So this is the correct results.
Yes, this is the correct result as far as I know, and it depends on. Can you go back a little bit, maybe 1 or 2 slides?
This.
Let me see where it says kill worst, where it has kill worst, where it says the function kill worst. Yeah, just back 1. Yeah, kill worst. How the kill worst function. So this question, the kill worst, it'll achieve that equilibrium if this would work in nature, if kill worst would actually happen in nature, you'd get that equilibrium. And that's an active debate, whether kill worst actually happens in nature. And there's some subtleties to this. And that's what led me to my discussion about the definition of fitness that I had with, not just with Dapper Dino, but I had this discussion before. Because in nature, we can have genetic deterioration, like say with blind cavefish or certain other diseases that would actually be selectively favored. But in terms of what we would call function, in terms of like kind of mechanical capability, that's where kill worst may not actually work. And so this is still an open debate. But what
you mean sort of negative selection, that the feature is selected for, but this feature reduces the functionality of organism. Yes,
Right. That's what we call, yeah, that's what we call reductive evolution.
Mhm.
And the framing of the creationist argument, just to put this in context, because some of these questions came up with creationists, and also in Michael Behe's book, Darwin Devolves. This is kind of an important question. If there is deterioration in the functional sense, it may actually be, in the reproductive sense, it may be getting more fit, but in the functional sense, it may be losing genes. And this is where the discussion, unfortunately, kind of goes away from the pure math, which you've done. Your math is just perfect. It's beautiful. The question of, because so much population genetics is focused just on reproductive rates rather than functionality, that's where there's a little bit of a disconnect with what it means to actually degenerate, for a genome to degenerate. So the word deleterious in population genetics is not kind of the same notion in engineering. So it was because of this phenomenon that you've articulated well that I began looking at the question of definition of fitness. Now, you've articulated this way better than I ever did. I just kind of knew it intuitively, what you put in this presentation, but I couldn't articulate it as well as you did today. That's why I really liked your presentation. And that raised this question of what we call, what you call the kill worst function. They call that truncation selection. And Mendel's accountant tried to model that question of truncation selection. I didn't explore it that much. And the thing about Mendel's accountant, their definition of fitness was still the evolutionary definition. It wasn't the functional definition. So you articulated what I sort of knew intuitively. You did it a lot more rigorously than I did. This is a lot clearer. That's why I really liked your work.
Yes, thanks. But I don't know, is it too, so here I just truncate units would have more amount of mutations. And I just actually, can you think or can you not that if unit have more deleterious mutation, it will be harmful for him in both functional and reproductive sense? Like that. Now I said I cannot really get how to improve this.
You know, maybe the best thing is, if you find the literature, I'd be grateful. I unfortunately, I'm spending a lot more time. A lot of my focus will not be population genetics. Mine will be mostly in chemistry and cell biology. And
what literature, for example?
I'm sorry.
What literature you mean?
So if you can find, because I have no idea how to begin how to search for this literature. I know it must be out there somewhere. If I find it, I'll also let you know if you find something. But you know what? Maybe just to, if we have a minute here, I'm going to try. Let's see. Truncation. I'm going to look truncation selection and equilibrium. Some population geneticist knows. There is what they call, there's the word mutation selection balance. Maybe that will get you what, and again, that's not something I'm that familiar with, the mutation selection balance. I've heard that term, mutation selection balance. Let me just look that, mutation selection. This could be the wrong thing. Okay, mutation selection balance is an equilibrium in the number of deleterious alleles in a population that occurs when the rate at which deleterious alleles are created by mutation equals the rate at which deleterious alleles are eliminated by selection.
Oh, yes.
That might be where to start. So
Okay, thanks.
maybe again, I kind of just, it's because I had issues with the definition of fitness that I sort of just stopped right there. But what we can do, you've sparked my interest that just for completeness, I should look this up, learn a little bit. I need to learn a little bit more about mutation selection balance.
Okay, sure.
So this was
was
excellent. This was an excellent presentation.
Thanks.
So I wanted to thank you for that. So I'm sorry I have some, I haven't probably, we probably haven't tied up every loose end. And there's some areas we probably collectively, you and I might have to look in to learn to explore more of these questions.
Yes,
And then also professionally, I might be writing a little more on this. It would be good for me to at least put it in writing and then publish it in one of these small ID-friendly journals or just an educational article that's just released on the
yes,
public.
sure. You are free to use all this stuff. Yes.
So, did you have any closing thoughts? This was an excellent presentation.
Okay, I have not finished it because I wanted to. There is some other slides.
Oh, please go on.
Go
on.
I made a long run and like put in at the begin huge amount of mutation, and I view. And what I have seen at the begin, this increases, and then some sort of equilibrium is reached, as you said. And if I put the amount of, so actually with 80 mutation per unit, it is reached something like that. And if I put very low mutation rate per unit, like 3 mutation per unit, it goes down and stabilizes at a low level, like 20. From maximum I have 2000 mutation for a unit. Okay. And actually you can, in my simulation, you can adjust actually different parameters, like can the mutation be reversed, like from one can to 0. I have not made that, but it's possible to plug in, because I count the worst case scenario that mutation cannot mutate back to the original situation because it's improbable. Am I right?
I think so.
Okay.
Yeah, that looks very nice. And oh, by the way, Peter, if there's a way you can make your slides, if you could send me the links where people can access your slideshow and your your Python programs, that would be great. I'll put it in the video description so they can access it.
Okay, I will make the Python project, but the stuff is I have sort of reconstructed the program so it does some additional features, because this program is made sort of tutorial and
right.
Program like you can see from the structure. So
now
yes, I can do the like Git repository, and I will show the presentation and Python files, and as I want, I will change a little bit and people can watch it, because I was actually prepared to talk about the programs, but I have actually changed it a little bit. So added some stuff, but I will not talk at there now because it's not sent to you and so on. Okay, we will make that. Okay. I will post you later the Git repository link.
Okay, that'd be great. And we might be able to revisit this question again. See, now you've sparked my interest in the mutation selection balance question. I don't know if it's related, so apologies to the readers if I'm specifying something that's not accurate. But that's the closest thing I can think of. And if you find, Peter, if you find something, there's a Wikipedia article on mutation selection balance. If you think that reflects what you've shared today, that would be a valuable thing for me to know.
Okay.
And because this is something I've not delved into very deeply for the reasons I mentioned regarding the definition of fitness.
Yes, as far as I know, I have heard recently about some work about truncated selection and so on. I can add it too a little bit. That's I am not sure what it does, although it's some truncation selection model from a couple of years ago. Maybe you heard something about it. Oh, okay.
Well, we can have another show sometime, and
yeah, sure. We can make sure where we sort of read and discuss papers.
Yes. So I just want to update you. My schedule is going to be pretty busy for like the next couple of months.
It's no problem. Just say.
But I think we covered a lot of ground in our in the shows we've had together, and including this one, and a lot of interesting material. And there are some questions that, some issues you've raised and things we've discussed that are important to me professionally. Because I'm also trying to teach a little bit of math. And so I learned a little bit of math through this presentation too. I'd like to go through the proof of the relationship of the Poisson and binomial distribution. I'm familiar with the binomial just because that's casino math. So that's interesting in and of itself. So maybe in a couple months we can have another show. You'll see on my channel, I'll be focusing a lot on chemistry and molecular biology and cell biology. I'm having to learn that.
Yes, I watch your channel. It's really great.
Yeah. So that'll be kind of my focus over the coming year, because I need to just get reacquainted with the basics. Just by actually teaching it, that's how I'll learn things. So I wanted to thank you for watching those videos. I may be moving to a different platform for some of my educational work rather than YouTube. That'll give me some freedom. So that's just a heads up. That's a decision that I made to over the last day. But I really look forward to interacting with you more. And do you have any final thoughts before I shut down the discussion?
I wanted to. We want to finish this because maybe I got some questions. So
Sure.
some short questions. So how to add more details to this model so it will be more reflecting the reality? What do you think?
How to add more details? Actually, you've actually shown more details than any model that I've built. And I don't have a good answer for that. One thing that I'll point out, even as far as probably the most important detail that I'm still working on professionally, is the issue of what would constitute kill worst.
Yes.
Because then that goes into the definition of fitness, and that's still a kind of an open question, because we can there are experimental things that we see, like when bacteria are losing genes. It's like, well, you know, we can say that the bacteria are getting beneficial mutations when they lose genes, and I don't know how we can actually model that, because clearly we would consider that a genetic loss. And that's probably the more important thing that needs to be resolved. And certainly the population geneticists and evolutionary biologists don't like this redefinition. But on the other hand, people that are actually looking at genomes and seeing genes being lost, I'll give a specific example. The E. coli, it can lose 80% of its genes and survive, and it may actually be selectively favored because it's lost 80% of its genes. Now, in the case of bacteria, they can do horizontal gene transfer, so they can actually get back the genes that they've lost. But for other organisms, like, say, humans, that's not really feasible. And so that's the more important detail that I'm focused on. So some of the smaller things, like when you're trying to model the genomes, like with the mating of the parents, the mother and the father, I think your model was good enough as far as that goes.
Okay. So what I wanted to say, how do you think must the genetic entropy effect be observed in the genetic algorithms in machine learning? So what is happening there is you simulate in the computer some sort of game where units perform some task, and the units what perform the task better are positively selected, and the children of they are mating, and children of those get new mutation what change their behavior, and that's how this actually genetic algorithms works. And it works because there is a valid solution of that. I actually observed some games. What are of those? I can actually. It is some Neuro Evolution project, Amoebas project, and so on. There is some usage of it, like if you want to modulate, if you have a skeleton and you want to modulate its behavior, you just run the physical simulation of the skeletons with muscles, and the best units will be selected. So it's how the movements are constructed in the simulation, for example. It's one usage of it. So do you think that genetic entropy must be viewed in this kind of populations?
Yes, I actually, it depends on the construction of the genetic algorithm. This was an interesting question that I actually was invited to study way back like 13 years ago. I was going to work at the Evolution Informatics Lab with Bill Dembski and Robert Marks. These were, at the time, they were like some of the most foremost ID proponents. Those names are not mentioned very much today, but they were looking at the question of genetic algorithms like Avida and Tierra. And there was also there are two other doctoral students, Winston Ewart and Eric Holloway, who looked at this question. I worked on it a little bit. So must genetic entropy be observed in genetic algorithms in machine learning? So let's take the one with genetic algorithms. If you can, like in Avida, when increase in complexity was rewarded, we didn't see genetic entropy. One could write a genetic algorithm that favors reproductive speed in throwing away genes. And I actually started to write an algorithm like that where, okay, let's see if we can, if we rewarded simplicity, we would see genetic entropy. That would be like Darwin devolves. And we have had experimental evidence to that effect on many levels. That's what they call reductive evolution. So we've seen it both experimentally, and then we've had models of it. There have been some people that wrote some computational models of reductive evolution. We see it particularly in parasites. A good example is like a tapeworm. Once it gets inside the host organism, the tapeworm starts losing its organs because it doesn't need them. It's able to feed off the host. So to answer that question, it doesn't always have to be. It could go either way. So we could write genetic algorithms that will create genetic entropy. But that's not of interest for a lot of people professionally who use genetic algorithms to solve technical problems. Like, I don't think, like a famous genetic algorithm is the traveling salesman. That probably wouldn't apply. You wouldn't see genetic entropy there. So it would depend on the application. That's kind of my best estimate of, as far as an answer to that particular question.
Yes, but because it is so, it must be considered just from the view of informatics that this is possible. So if you revert the increased complexity, it must not happen. You would say that. To put it short, right?
I'm sorry, I didn't.
If you, so you have said that if you revert increased complexity of units, then the genetic entropy must not happen.
Correct. We saw that with Avita. We saw that, and actually there was, in the old Avita software, there were some funny things that I did. I could switch the parameters so that it would reward simplicity, but then they changed their software. So it's genetic entropy in kind of man-made algorithms. It doesn't happen all the time in man-made algorithms.
Okay, I got it. Also, it is running poorly. Sorry, I would ask you questions. How to determine if so? It's again this question: how do you determine in the lab if the genome is functional or dysfunctional, and how do you mark the places of the DNA that they are functional or dysfunctional?
That is still an open question, and the way that we've been trying to determine it is the medical researchers, if I could relate this, they actually are still trying to determine it. And one way that they began to arrive at it, just experimentally and observationally, is a lot of the medical researchers noticed that the patients with heritable diseases, like say diabetes or some other disease, it was correlated to changes, to mutations in their, in what they call junk DNA. Now, it could be that that's just a coincidence, or that the heritable disease caused the mutation. But they have, as they researched this, they were able to determine that it had the mutations in the junk DNA were causing the disease. So that's kind of like how we find out. We actually don't know it ahead of time, and I keep seeing new papers, just like almost every year, that will say, okay, this section that we thought didn't do anything, we see that it has some role in one particular cell type. So we have different kinds of cells in the body, like skin cells, bone cells, cells for the eye, for the liver, the kidney. Some of these stretches of DNA are only significant in certain cell types, and also at certain stages of the organism's development. There are some parts of DNA that are only used for 3 hours. For 3 hours in the entire life of an organism. So like in the embryo stage, there are some genes that are only turned on just for 3 hours, and it's never turned on again, but they're very critical. And so it becomes really difficult to establish function. So right now, everyone is just kind of guessing, and we've not been able to determine it. So they're faith assumptions on both sides of the question, between the medical researchers and some evolutionary biologists. I don't think either side is going to be able to absolutely prove their point. The only thing that we can actually measure is whether our health is declining in terms of more birth defects and heritable diseases. That's about the only thing we can measure. We can't, it's very hard to actually determine whether these fractions of the genome are actually functional. We can make our best arguments, and that's about it. No, there's no one on the planet that can actually give you a figure and prove it.
Okay, thanks. So may I ask you
Sure.
to link or send me some of related paper about you told that junk DNA appears to be functional? That would be great. It's very interesting.
I don't have a single paper. It is part of my professional responsibility to start compiling it. And I may post, now that I'm moving a lot of my stuff away from just the YouTube channel to my website, I'll try to remember to, as I compile this, to keep you updated as I get the papers. Unfortunately, a lot of the papers are very, very technical, but I will try, I'll try to maintain that, and it should be a public thing. That's something that I've been actually tasked to do, is to collect papers on the functionality of DNA. And so I can specifically give you one example of something they thought was junk that turned out to be really, really important. It was a breakthrough. Yes. It was called the hot air link RNA. Hot air. You know, I may give a video. Let me, can you give me a moment? I'm going to put this on my list of to-dos.
Okay.
I'm going to put a presentation. Let me say this. I need to make a presentation on hot air. Okay, let me just put that on my list. And the reason it would be worth to see it, the hot air link RNA is only, it's only one small fraction of the genome, but it took like 20 researchers an entire year just to establish it was functional. And so the problem in establishing if something is functional, it's like we could probably be spending the next 10,000 years. If at that rate if it takes that much effort just to get a small piece of the genome to establish it's functional, well, we have our work cut out for us. But it would still be good to show it, because for a long time it was thought to be functionless. So that might be educational in itself, just to see how difficult it is to actually conclusively prove something is functional.
Yes, that would be perfect. Yes.
Yeah. So I may give a talk on that. And so unfortunately, I think the arguments are going to continue, because we have a lot of speculation. We don't have enough data, and that's not a good situation, but that's the situation we're in.
Yes.
You had something here. You said you don't consider the mutated loci to become functional again. Okay, thank you. I appreciate that. Okay. Do you have any other questions, Peter?
No, I think it is enough for now. And
yeah,
I see you also sort of.
All right. Well, God willing, we'll talk again. And
yes.
I'm glad you're one of my favorite people to talk to.
Thank you too. So.
Yeah, because you really like these very detailed and math topics. And again, I want to congratulate you on your presentation. You articulated something that I've sort of intuitively understood, but I could not express it. You did a much better job of presenting it than I could have. So thank you. So I'd like to thank, I'd like to thank all the viewers for joining us today. And Peter, until we meet again, you take care.
Yes, you too.